Happy Thursday afternoon. Continuing on, right? We were doing tangent lines. Every time you need a line, you always need to find the slope. So remind me, how did you find the slope of a tangent line? What is the slope of a tangent?
Is it a derivative?
What's the derivative? Oh, no, this was said, can you blame the weekend? Just did it on Tuesday.
Limit of x to a over the f of x minus f of a over x minus a.
What is f of -1? That's the one we're looking at. Can we simplify the numerator?
I don't think so.
Oh, we can. What are we going to have to do to evaluate this limit? Right now we have 0 over 0. So it's a technique that is used in algebra.
Multiply by the time period.
It's called rationalization. Except we're rationalizing the numerator, not the denominator. Now recall that rationalizing doesn't change the value. Because all we're doing is multiplying by 1. Numerator. It's a difference of squares now. So it's just 3x plus 5 minus 2, right? The denominator, however, is going to be hideous. Factor out of 3 from the numerator. Then what we're left with is this limit. What's that limit? How'd you get 1/2? Who gave me the 1/2? Be honest. How'd you get it?
It isn't right. But
Wow. How'd you get it?
I looked at the two, square root of 2 plus square root of 2, and I immediately got multiplication. And I thought multiply together.
Okay, yeah.
Wouldn't the correct answer be 3 over 2?
3/2? How do you get that?
You put in -1 for x, get -3 plus 5 square root of 2 plus square root of 2. Then you multiply the n by 3, but somewhere along the line you messed up.
Was it 3 over 2 times square root of 2?
3/2√2. Or if you don't like that, you can rationalize it. I don't care. I probably will, since it's just constants. tangent line, remember, was y equals what form did I give it? Did I do the plus f of a at the end or first? I don't remember. I think it was that, wasn't it? Slope times x minus a plus f of a. Three root 2 over 4 plus root 2. So 3/4 plus 1 essentially.
Is it 7 square root 2 or 4?
Just 7 root 2 over 4.
Here.
And there's our tangent line. Switch over here. We just said it's tangent line. 3 square root of 2 over 4 all times x plus 7 root 2 over 4. That looks good. This time, square root's in the denominator. Oh, this will be fun. We get to deal with complex fraction. Limit as x approaches a.
Are we allowed to square, like for the last problem, would you be allowed to like square the entire equation? Or would that work?
What do you mean by square the entire equation?
Like the entire, like, fraction.
Just the fraction? Then no. Could you write it as y squared equals that entire thing squared? Yes. But how does that help you? Because then you have a binomial squared. Right? If it's what I think you're trying to say and you're just squaring each of the two terms, then no, that you can't do. That you. Limit as x approaches -1. F of x minus, what's f of -1? Uh-oh. Undefined. Uh-oh.
Well, then we'll just keep it in the square root then.
That's why. That's not supposed to be a -1.
Oh, okay.
That's what it's supposed to be.
Ooh, that's very different.
It's got to change the value apparently. What's f of 4? What is it?
1/3.
1/3. All over x minus 4. How did we simplify complex fractions?
Can we do that yet if we're subtracting the numerator?
Hmm?
Can we even simplify complex fraction if we're subtracting? Yeah.
Yeah, you can always simplify a complex fraction. In fact, we did it twice on Tuesday. It was the last two problems we did on Tuesday.
Multiply by the LCD.
What's the least common denominator? Just that? I agree that's in the LCD. Which leaves us with 3 minus square root of 2x plus 1. Did that resolve the indeterminate? No, which means we have to do what? We have to rationalize it. Which means that denominator is going to be absolutely hideous. first. 3 square root times x minus 4 times 3 plus square root. What are we left with in the numerator?
N minus 2x.
What was it?
N minus 2x.
How did you get 10? That's what I thought. Is it 9 plus 1? Should be 9 minus 1. Now. Oops. That one cut. Is it going to let me? No. Oh. Thought I was being clever. Oh, that's unfortunate. Do that. Instructor's prerogative. I'm not rewriting that whole denominator. So how can we simplify the numerator?
You got it too.
Go one step further. Just taking out 2 is not going to help.
Yeah, negative 2.
I got a negative 2. Leave us with x minus 4. Okay, that will leave us negative 2 times the limit. 3 square root times 3 plus square root. Denominator, all under 1. What is that limit? What is it? 1 over what?
Negative 2 over 54.
So your limit was 1 over 54, right? Okay. Now why does negative 2 over 54 make me sad?
Because it's not the least complicated fraction.
Reduced.
Least
So reduce it.
negative 1 over 27.
And fair warning, if you don't reduce your fractions on the test, you will lose points. I've had it happen where they forgot to reduce one fraction, and that's what cost them a 100.
Wouldn't just factoring out the 2 before, because I think before the numerator was 8 minus 2x. So if you just took out the 2, wouldn't it just be x minus 4? And then
No. It'd be 4 minus x. if you just took out a 2. Right, factor out 2 from the 8, and then from the negative 2x. You're left with 4 minus x, not x minus 4. Which doesn't cancel. That's why I took out a negative.
Yeah, that makes sense.
You could theoretically not do that and just realize that 4 over x over x, or 4 minus x over x minus 4 is negative 1. You could realize that as well, which is the same effect. Right? See that? Four 27ths plus a third. Do the hard part. So 4 27ths plus a third. So there's the tangent line. Would that be acceptable?
Can't simplify it any further.
Yeah, that's acceptable. That's not slope-intercept form, but it's still acceptable. Right? Function was what? 1 over square root 2x plus 1 tangent line x over 27 negative plus 13 over 27. I don't really like that view. That view's better. Now I didn't show. But I'll show it now. I didn't show the last time. the point on there as well. And the point was what? X equals 4 1/3 was the y, right? So obviously you know what this is going to do, right? That just gives the plot. This will just give me a point at that ordered pair, 4 1/3. I'm just defining these now as variables. Because if I don't do that, if I just execute it like this, that's what it gives. But I want to get them on the same axis. Show command. Now you have to be careful with the show command, because it does give priority to what comes first. So the order in which you put the show in determines its priority. This plot takes priority. Then second in the priority list would be the point if there was a third one, right? Then obviously the point would be higher priority than what came after it. And so I could also plot the point on there as well if I really wanted to. I can also put a color to make the point. And again, you have to be be careful with the graphics option, because again, that order does matter. The options for your point have to come first, and then your point, which is kind of weird, but that's the language. So let's go just a simple function. Tangent of x. Find the slope of tangent of x at pi over 4. You take the limit of what? Tangent of x minus 1 over x minus pi over 4. Find that limit. Even something as simple as that's kind of a headache, right? Let's go even more complicated. Tangent of the natural log of the secant squared of x. find its slope at 3. Oh, you're gonna have a lot of fun with that one. So clearly this isn't ideal. We want a quicker way to find the slope. To do that, we want to determine, okay, well, can we write slope as a function? Right, so not just now finding slope at some point. Can we find a slope function that we could then evaluate at the point of interest? We call that the derivative function. So a quick note on terminology. A lot of the time, you're asked to find the derivative. This is what they're referring to. What we're about to do is not a derivative. A derivative is a constant. It represents slope. What we're doing is the derivative function, which is something different. And that's how it's defined. It's the limit as as h approaches 0 of f of x plus h minus f of x all over h. Again, you might see h replaced with delta x.
Wait, so what does this function do?
This gives us the slope as a function of x. So that then I can just go, okay, now we have slope as a function, find the slope of f at several points. And you don't have to do the limit every time. You found the function. Now you just evaluate that function at those points, and that'll give you slope. So it's a shortcut.
But you still have to find this function for each individual other function.
Yes.
Okay.
But we're going to be using this to shorten it even further.
Isn't that basically just the difference quotient?
It is, isn't it?
Yeah, how does that differ?
What do you mean, how does it differ?
Because wouldn't the difference quotient theoretically just give you m? And that's always
So difference quotient gives you slope, but slope of what? Not the tangent line,
secant.
of a secant line, which is not what we're interested in. We're interested in the slope of a function at a point, which is the slope of the tangent line at that point. That's why we have to pass it through a limit. Right, but that is what we're doing, right? We're
So
taking the limit. We're essentially just doing a bunch of secant lines.
if difference quotient's giving you m as in a secant line, not as in a function, why in this case is it
Well,
a function instead of
So you could, so slope of a secant line would also give you, or you could also get a slope function of a secant line, just as the difference quotient. But the problem is then you have to worry about, now what's the incremental change in x? Right, so what it would be doing is you'd be fixing a point and then determining, okay, so what's the slope if I move the point half a unit to the right? That'd be h. In that case, h would be plus 1/2. So the difference quotient does give you a function as well. But we're now taking the limit of that function as your increment goes to 0. That's what the tangent line slope function is. Versus what we were doing before was finding it at a specific point, right? So we already had that point, and we were then just letting the secant line points converge onto that one point of interest. Now we're just doing it for an arbitrarily chosen point. X. Right, remember this discussion? That's what we're doing. Except we're now letting A be X plus H.
It makes sense.
Right. What do I want to do? Brings that back. Bring that up. That is red F prime of X, right? Do I Oh, I do, okay. I'll go with that later. Now, of course, it's a function, which means it has a domain. And its domain is all the values of X where that limit exists. Which brings in the idea of differentiability. What does it mean for a function to be differentiable? Well, differentiable at A if f prime of A exists. And then more generally, we say the function is differentiable on an interval S if it is differentiable at every point in S. We say a function is differentiable if f prime of x exists over its entire domain. So the domain of the derivative function is the same as the domain of the function itself. Then we say the function is differentiable. Here's an important result. Let f of x be differentiable at A. Then it is continuous at A. So differentiability implies continuity. What about the other way around? If a function is continuous, does that automatically mean it's differentiable?
No.
Can you think of a function where you have a point where it's continuous at a point but not differentiable at that point? Where would it it be continuous at but not differentiable? Which would be what point? X equals what?
0.
The absolute value of x, continuous at 0 but not differentiable there. Now, is there a function continuous everywhere but differentiable nowhere? What do we think? Is that possible? Said no? Makes sense for a function not to exist like that, right? Because it just basically means just a bunch of jagged edges, jagged vertices. Sadly, you're wrong. There are functions that exist that are continuous everywhere but differentiable nowhere. This is one such function. It's called the Weierstrass function. Pick any point, zoom in, it looks the exact same.
What's the equation for that?
I'm so glad you asked.
See it better when you do that.
It is defined as a Fourier series. There we go. As a Fourier series. Go away.
And when are we going to work with this function?
Are you a math major?
No.
Probably never.
Okay.
Are you an engineer? No chance.
Computer science.
You won't even deal with Fourier series. You're my physics person, right? You will be. I don't think you deal with this function, but you'll be dealing with Fourier series. Oh, you'll find out. Take partial differential equations. You're going to need it. Right. So the proper question, the proper answer is, who cares if we ever use it? It exists and it's cool. That's the answer for mathematics.
How's it going from parabolic to jagged?
So it's based on the value for b increasing from 0.1 to 5. So a and b are integers. Or not, I'm not sorry, not integers. A is a real number between 0 and 1. B is any odd integer. Any positive odd integer that satisfies this condition down here. So what this graph is doing is just letting b range over its possible values. So that's what's happening here. So when b is small, it is just parabolic. But as b gets larger, that's when the interesting stuff happens. And I think they held a constant here, didn't they? Yeah. And it has to do with the fact that, remember, this is a summation. It's an infinite summation, which is why it's changing it so drastically. I can make an assignment on the Weierstrass function.
If that's an infinite summation, does that mean that it's adding every possible permutation of what could happen as B is getting smaller?
No, so what the infinite sum, first you pick values for A and B, and then you sum. So what's being summed is n. So you have fixed values for A and B in terms of summation.
I give it up.
Right, so the actual summation itself, your A and B won't change. But you can choose different values for A and B. So this is technically a three-variate function. You have your x, which is the true variable that acts as your function, but then you also have variables A and B that you can fix values for. Kind of like when you write pi r squared. No, that's not. I'm trying to be a good example. I don't know if we've encountered anything yet that I really compare it to. You'll study summation more in Calc 2. Infinite summations in Calc 2. It might make more sense then. But for now, just realize that A and B are some constants that once you pick them are fixed for the problem. So they're just arbitrary constants. So we have this is a family of functions, really. And we'll actually see a constant again when we study integration. Get a family of solutions for integrals. Yeah, but yeah, I wouldn't worry too much about this function right now. This function is definitely beyond the scope of this course for analysis. It's just an interesting function that's continuous ever on differentiable nowhere. Maybe I will sign the project on it. Make you read up on it. Here's another interesting tidbit. Who invented calculus?
Trick question. One of those things where we think we know the answer, but it was actually someone else.
So I guess invented is wrong. Discovered, maybe, would be the right word. Who discovered calculus?
Wasn't it Isaac Newton, or it's this one German guy, I forget his name.
Who's credited? Newton's credited, but it's not Newton. Someone actually submitted their paper before Newton did. His name is Leibniz. So why doesn't Leibniz get the credit? Because Newton was a dick. The head of the society that published papers was Newton. So he he turned down that first submission for his own. And generally speaking, that is how a lot of discoveries go. It's not the person who discovered it who gets credit, it's the one who's more famous. But we give Leibniz an honorable mention. So Leibniz notation, dy dx, would be y prime. That's known as Leibniz notation. It's used interchangeably, depending on the situation. Oh, well, we took a derivative, right? Y prime, let's call it. It's a function. Doesn't it have slope? So we take its derivative. That's the second derivative.
In this class, are we going to be finding the derivative of derivative functions?
Oh yeah, we'll be doing higher order derivatives.
What's the application for that?
We'll study it. There's graphical applications that we're going to study. Also physics. Ever heard of a little thing called acceleration? That's the second derivative. Right, acceleration is the rate of change of velocity, but velocity is rate of change of position. So acceleration is the second derivative of position. Okay, physics guy, what's the rate of change of acceleration?
Jerk.
It's the jerk. That's called a third derivative. What's the rate of change of jerk? This is actually funny. This again is just completely useless knowledge because you never use it in physics. But it's knowledge that's out there. The snap.
Makes sense. So we're going to be doing higher order derivatives. Are we going to be using this notation?
I'll be using these notations interchangeably, yes.
Okay. I don't know what I'm looking at.
It'd be better if I do this. So this tells you the order. And all this is saying is it's derivative of the derivative. Right, so if I do cubed, it'd be the derivative of the second derivative, which would be nested, right? So it'd be, this would go in there. Right, so that's all this 3 is saying, is that you're applying it 3 times. And then you have y double prime, y triple prime again, it's just saying you're differentiating multiple times. Rate of change of the snap. It's even better. Crackle. Rate of change of the crackle. Yep, is the pop.
Who named these?
I don't know, but obviously someone who was really in the mood for Rice Krispies. And that's not a joke. You can look it up. That's actually a thing in physics. Because I thought it was a joke, and so I looked it up and verified it. It's a real thing. In general, we'd write the nth derivative this way. Yeah, and by the way, there's names for things that come before position too. Because position is a rate of change. Again, completely useless because you never do it in physics, but I don't remember. because it wasn't as interesting as Snap, Crackle, and Pop. So limit as h approaches 0. F of x plus h. Minus f of x all over h. And once again, by its very nature, if you do substitution, you're going to get 0 over 0. Which means we have to do algebra. Get 4 plus 8x plus 8h, right? Distribute that h through. X plus h quantity squared. It's a known formula. It's a special formula in algebra. X squared plus 2xh plus h squared. And then just distribute that -5 through. Distribute the negative through that second function. Fours drop out, 8x drops out, 5x squared drops out. Every term we're left with has an h in common. So I'm going to factor out an h as well. And we're left with 8 minus 10x minus 5h squared all over h. Not 5h squared, sorry, 5h. And that was all pre-calculus, right? Because that was the difference quotient. Now we get to apply calculus. What's that limit? What was it?
I did the inverse.
Minus 10x plus 8 minus 10x. Calculus is easy.
That's our derivative.
That's your derivative function.
Right?
And did I mention it? I don't know if I mentioned it in this class. You have to be careful with how you cross out your h's, because that is a thing. It's the reduced Planck constant, which is to physics. Learning in quantum mechanics.
So finding higher order derivatives would be doing that multiple times.
Yeah, then you'd have to do the limit of the difference quotient of 8 minus 10x for the second derivative.
Okay, so that actually doesn't seem too bad. Just seems like a lot.
Yeah. It doesn't seem too bad. Depending on the function, it isn't. It's just extremely tedious.
No shorthand?
For the most part, I'm not going to do higher order derivatives with the definition because it is just a pain.
Is there a shortcut for it, or is it just?
There is, and that's why we're studying this first, because I'm going to be using this definition to derive all the shortcuts. Well, the battle's starting for someone. That's telling me that my Calc 3 class is coming up. Have a good weekend. We'll finish this up on Monday.